famous. Nelson Natalie Man. Natalie, unfortunately, what do you say from screen? Homework 2. Homework 2. I have to see your submission homework 1 wonderfully. Everybody except for one student submitted on sign. I think it's one person maybe dropped out. Yes. But anyway, we don't stop here. As you can see, homework number 2 is available. Due is next Friday. Next Monday, we're going to have class. But the due is next Friday. If you see the first question, we have done. Last Wednesday, I showed you. That's what the first question is. Those numbers are different, so please use this documentation for your homework. Those input numbers are a little different than what we have done in the Wednesday class. So please use this homework documentation for your homework. And question number 2, question number 3, I will show you today. How nice I am, baby. I will show you today. What that means, try to finish today and then go watch football tomorrow. That's what we do. Yeah? So please, don't postpone doing it. Why? You don't try today, you will forget what to do. So, I don't make recordings, I'm sorry, but if recordings are available, I know it's too easy for you guys. It's solution there, you don't try hard. For learning software, as I mentioned several of you, you need to agonize all night long. Spend all night long to figure it out. Then this software becomes yours, truly. If you do not go that process, you just copy from recordings or from solutions, this software does not become truly yours. So please understand, try to spend more time, put more effort to finishing your practice and homework questions. Yes? Okay? Try to do today, please. If you don't, you will forget.
We should work on our slide today for lunch.
Okay, what we do, we look at it, it's called liquid expression. In other words, or solvent expression. Liquid extraction is used in many chemical industries, such as coffee manufacturing, production of fine organic compounds, processing of perfumes, production of vegetable oils, production of food flavor agents. As you can see, liquid extraction or solvent extraction is used in many chemical industries. Our process description is we have mixture, water and MEK, methyl ketone, MEK. So we have mixture of water and MEK. We are going to use octanol as a solvent to enhance the separation of water and MEK. Our main goal of this modeling is to first carry out a sensitivity analysis by varying the mass flow rate of MEK, methyl ketone, in feed stream from 1 to 21 kg per hour to find out what is the best property method for this system. So the first objective here is to carry out a sensitivity analysis to find out the best property method for this system. So that's the first goal of today's modeling. And to separate the feed stream means water MEK mixture into two pure streams. For example, 99.8% pure water, and then additionally we will use distillation column to get 99.9% purity of ethanol. That's our objectives is in. So let me tell you again, we are going to carry out a sensitivity analysis to find out the best property method for the system. That's the first objective. Then we will try to get or separate water MEK mixture to pure water and pure octanol using pure water, pure MEK using octanol. But our target is to get 99.8% pure water and then 99.9% pure octanol. Of course, we will get very pure MEK as well. So the process flow sheet looks like this. We will learn new unit block is called extract. So the first ET-1, that's the new block, is called extract block. We will learn this one. So as you can see, we have water MEK mixture. We use octanol to enhance the separation. Then from this extract block, we will get top product, bottom product. We call top product as extract and bottom product as raffinate. From the bottom product, as you can see, we get pure water. Then from the extract, we will have MEK octanol mixture. MEK octanol mixture is a totally different boiling point. So simply we use distillation column to get pure MEK from top product and pure octanol from bottom product. Is it clear? Okay. Can anyone explain us what are our objectives today? Natalie, Sean, Natalie, either one. Let's do Sean. I think Sean was best, right? Sean.
To figure out how to get 99% weight or 99% octanol through this process, but also to figure out what property method would result in the easiest goal for octanol, or the most efficient goal for octanol.
Wonderful. Good. Natalie, can you rephrase a little more? Can you rephrase? Oh.
Do sensitivity analysis to find the best process.
Yes, we carry out sensitivity analysis to find out the best property method. That's the first objective. Then Sean explained it to get pure water and octanol. But the first objective is to carry out a sensitivity analysis to find out the best property method. What best property method we are talking about? What kind of property method we are talking about? Neil.
SRK or something?
Huh?
Like something like SRK?
Okay, SRK, NRPA, Unifact, those are property methods. Which property method is the best for this system? That's what we are looking for, eh? By carrying out a sensitivity analysis. So let's look at it first. Even though our flow sheet looks like this, first, okay, what kind of property method we are considering for this system? This property method validation network gives us some idea what property method is the best for this system. So if you look at this network, there are two different ways. Activity coefficient based model, you can look at it, this bottom network. And then equation of the state based model, you can look at it, the upper side of the network. So if you look at the bottom, if you are dealing with polar component, for example, if you are dealing with polar component, water is a polar component, okay? You can Google it, whether this component is polar or non-polar. If you are dealing with polar component, yes, then you just follow this network, bottom side. So let's continue. If you are dealing with high pressure means more than 10 bar, less than 10 bar, low pressure. If you are dealing with low pressure or high pressure, just follow the network. Let's say our pressure is low pressure, so I can follow the uppercase. Then if you look at here, is that the interaction parameter available? Yes or no, just follow. Then we can see, we are dealing with polar component. Our operation pressure is low. Interaction parameters are not available. Whatever you follow that, maybe we can use NRTL property method, or we can look at a Unipeg property method and Unipeg property method. So by looking at this network chart, we have some idea. Well, there are many property methods are recommended for this system, but let's look at three different property methods for our system evaluation.
Is an interaction parameter, is that an activity coefficient?
I couldn't understand the last one.
Is an interaction parameter the same thing as activity coefficient?
No, it's a different thing. Okay, you know, so how Aspen works, how Aspen find out those thermodynamic properties, transport properties, kinetic properties. How Aspen find out? Aspen use binary interaction parameters. So even though you have three components, four components, Aspen only consider two components to find out those properties. It's called binary interaction parameters.
The checkbox that
You click that checkbox, estimate by Unipeg, that's the required for this course. That's what you practice. But the background, the theory, how Aspen find out those binary interaction parameters, right? Use two components to find out those properties. But anyway, so activity coefficient is different thing. Paging, activity coefficient is the measurement how much this component behave like non-ideal, deviate from the ideal behavior. That's called activity coefficient. So it's a different thing. But anyway, we can look at it three different property methods, and then we can look at which property method is the best for our system. But how can we find out which property method is the best for the system? We have to know some guideline or standard. Luckily, we have some information. What information we have? For example, maximum solubility of MEK in water is 21 kilogram MEK per 75 kilogram water at standard condition. 25 degrees Celsius, 180. Oh, we have that information. Somehow, we got this information, solubility. Solubility of MEK in water, or maximum solubility of MEK in water, is 21 kilogram MEK per 75 kilogram water. That information is given. Another information we can find out from literature review is called partition coefficient. So you can look at here, partition coefficient K, KOW means K partition coefficient between octanol phase and water phase. Another information from literature review is that the parameter partition coefficient K. How do we define partition coefficient? As you can see, partition coefficient is defined as the ratio of solubility of MEK in octanol phase to solubility of MEK in water phase. In other words, solubility of MEK in extract phase divided by solubility of MEK in reactant phase. Solubility of MEK, in other words, more concentration of MEK in extract phase divided by more concentration of MEK in reactant phase. That's the definition of partition coefficient. And from literature review, it looks like if we take the log of this partition coefficient, it's 0.49. If you look at here, 0.49 plus minus 0.04. From literature review, some engineers, they did experimental work to find out log partition coefficient is equal to 0.49 plus minus 0.05. Make sense? That's the experimental result. we do simulation. We look at simulation result compared to this experimental result, and which property method produce the closest number to that experimental result, which is log partition coefficient. Make sense? Please think. How do we find out? We can carry out a sensitivity analysis. What information is given? Then by varying the mass flow rate of MEK in feed stream from 1 to 21 kilogram per hour. So that information is given. We are going to use that information to carry out sensitivity analysis. Oh, page is sensitive now. Can you explain us? We are going to carry out sensitivity analysis to find out the best property method. But can you explain us what parameter we are using to find out the best property method?
Since we know what the experimental value of the partition coefficient actually is, if we use a specific property method, and that predicted or estimated partition coefficient, we can compare that to the experimental value.
Wonderful. Exactly. That's the logic is. Logic is log of partition coefficient is 0.49. We can set sensitivity analysis to find out exactly same log of partition coefficient and then get that value from simulation as using Aspen and compare to that experimental value, and then we can find out the best property method. As I said, we look at 3 different property methods. Make sense? Now, if you look at here, we are looking at partition coefficient. Look at the definition. What's the definition of partition coefficient? More concentration of MEK in extract phase. So we look at it, more concentration of MEK in this extract phase divided by more concentration of MEK in left phase. That's the partition coefficient. We just take base low, then that value should be close to 0.49. So we are doing some kind of math in Aspen. What we use for this simple math, we use Fortran, which is available in Aspen. So we are going to use Fortran available in Aspen to do very simple math. Yes? So I give you the equation here. First, we found the partition coefficient K in octanol phase, water phase. What is D? This is just guideline in Fortran when you define variable. In this case, double variable. Maybe you can use the character start from D to name the variable and then K of the partition coefficient. Now, experimental information is log. So log partition coefficient. First D is just Fortran guideline. When you name double variable, you start with a certain letter. That's called D. Okay. Where the information is available here, Fortran operators very similar to MATLAB. Only difference here, if you look at here, you use 2 stars for exponentiation. 1 star multiplication, 2 star exponentiation. Okay. Now some basic statement format very important here. And when you use Fortran available in Aspen, column 1 you can type C for any comment. Column 2 is left blank. But if you look at here, executable statement. Okay, you can check here. Executable statement begin at column 7 and beyond. That's very important. And no variables may begin with characters IZ or ZZ, so do not use these characters for variable name. And if you are defining integer variables, you can begin with letters I through N. Integer means whole number variable. So you don't have to worry about integer here. We are using real value or double variable. So real or double variables begin with letter A through H. I used D. You know, D, K, O, W, right? D, I used the letter D for double variables, no? Or real variables, no? And variables name are limited to 7 characters, and lower case characters are permitted. So those are basic statement format. We'll look at it in. But anyway, Brian, the first step, now we need to find out, or we need to carry out a sensitivity analysis to find out the best property method. So let's try to look at it. Is it clear? Great. Let's try to get Aspen. I will use specialty chemicals with metric. Please do your best to concentrate this lecture. No recordings available. Write down some memo. Take some notes. Okay? And then struggle all night long today to solve this question. You will improve it. So what kind of component we have? We have water. I will name H2O. We have MEK, methylketon, and we have octanol. Okay, 3 components. And if you go method assistant, if we follow the validation network, we already know we can choose activity coefficient based models, and default property method is NRTL. Of course, if you go here, there are many methods available. But let's look at it, NRTL property method first. Now we have 2 here. That's what the page was talking about. Estimate missing parameters by unit pair. Yes, whenever you see, just click that box. Okay? But in homework 1, we have tried regression analysis by retrieving data from NIST Institute. Right? That's what we have done in homework. Okay? But in this course, as I said, just that's enough. Okay? Let's make sure table generation completed. Means this property environment is okay. We can move to simulation environment. So I will go really quickly from now. So first, I will use very simple mixer. So if you go here, mixer, we have different shape of mixer. I can use that mixer. And as you know, we have 2 input streams and 2 output streams. Okay, so this one is H2O plus MEK mixture. We use octanol. And we name it this one as extract, and this one as methylene. Okay. And then I can pour this one mixer. Now, okay, let's continue quickly. So if you go here, we are working on H2O MEK mixture. All information is given. 25 degrees Celsius. Delight is fast to help me this one. Yeah. H2O 75. MEK 21. But those are all given, so I can go fast. Octanol 25 degrees Celsius. 1 atm and 100 kcal. Now if you click, we can do simulation, but what we are interested in, we are interested in mass fraction. So go to setup folder, go report options, stream tab, click mass fraction basis. Now if you just run the simulation here, you will see some warnings. Okay. Whenever you see warnings, do your best to fix it. Some warnings maybe you can ignore. It may not affect your simulation, but if you see some warnings, try to fix it. So what this warning means, we have free water, we have dirty water, we have dirty water in this case. What does free water mean? Free water, pure water. Dirty water. Water is in hydrocarbon. hydrocarbons are in water, then it's called dirty water. We are dealing with water with hydrocarbons, MEK, and organic, organic. So we have either dirty water. So in that case, I just show you, if you go setup directory specification, okay, setup directory folder and specifications, there is called free water. If you look at drop down arrow, there is called dirty water. You can take it over here. And if you go this mixer, just click mixer, the valid phases, vapor, liquid, free water, we have dirty water. Hydrocarbons in water, organic in water. So you have to choose vapor, liquid, dirty water. Yes? Huh? Maybe I can reset, let's look at it. Okay, I got no warnings, no errors. Now, if you look at here, we need to carry out sensitivity analysis. Huh? So if you look at navigation pane, it's called model analysis tool. Now you know sensitivity. So we click sensitivity analysis. Our first objective. Huh? So I click new S-1. If you look at here, we have 3 tabs to take care of. We need to vary something. Very simple. What do we vary? Mass flow what? MEK, wonderfully. So we vary mass flow MEK. MEK maximum solubility is 21 kg per hour in 75 kg of water. We are going to use that information. So what do we vary? We vary mass flow of MEK. So I click new, and then you can find out mass flow. And stream is H2O MEK feed stream. Component is MEK. And I says 1 to 21. By increment, maybe 1. That's what the setting is in vary. We vary MEK mass flow. Now, under define, what do we define? John.
The specific variables that we're actually changing, so like you define the flow rate as a variable like code like that.
I couldn't hear from the first part. Can you speak a little louder?
It's the variables for like mass flow rate, but it's the actual like in program variable that it needs to start varying.
Yes, so what we are looking for here? Well, what is our target?
To create a variable
We create a variable.
and then have it, and then basically use Tableau to define what it does to the variable.
So, but the question is, what do we define here? What
What block mass flow?
what variables we define?
What stream and what component we're looking at?
Anyone?
Is this the purity of the water?
Purity of water?
Partition coefficient?
Oh, partition coefficient. We are looking at partition coefficient. Yeah? Partition coefficient. We know experimental result. In Aspen, we are looking for partition coefficient. It's a good approach. Who said partition coefficient? Chase, can you explain us that?
We're using that, we're getting that variable to pretty much, we're defining that variable in a way where the program can calculate it, and then we compare that to the extra.
So can you tell us what's the definition of partition coefficient here? Quickly.
It's the ratio between the solubility of one component to the other. I don't know which
Okay,
one.
that's enough. Okay. So partition coefficient. We are looking at this one, partition coefficient, and in water phase and octanol phase, the OW. So partition coefficient in octanol phase and water phase. How do we define? It's the ratio of solubility of octanol divided by solubility of water. What solubility? MEK solubility. So what does that mean? We are looking for MEK solubility in extract phase, MEK solubility in raffinate phase. That's the definition of partition coefficient. Okay? In other words, what is solubility? We can say solubility same as mole concentration of MEK, methyl ethyl ketone, in extract phase divided by mole concentration of MEK in raffinate phase. Raffinate. That's the definition of partition coefficient. In the experimental world, they find out log partition coefficient, which is equal to 0.49. Simply, we are looking for this one. First, to find out partition coefficient, take a base log and compare to experimental result. So, on the definition tab, we need to define the partition coefficient. Yeah? Mole concentration. Now here, a little troublesome. Mole concentration of MEK. We need to specify that property or variable first. Mole concentration of MEK. How do we do it? If you go to property set, write down. Please, just take a note. If you go property set, there is called mole concentration. You go here, mole concentration, okay? But this is just mole concentration. We need to specify MEK. We are looking at mole concentration of MEK. So let's look at it, mole concentration in mole per liter. And then if you skip this one, you cannot get answer. But there's no red color. That's why it's a little confusing. Please take care of here. Qualifiers, you choose MEK. So we are looking at mole concentration of MEK. Yes? Now we are looking at partition coefficient. So we have to define two variables. Mole concentration of MEK in extract phase. Okay? Let's look at it. That's a stream variable, mole concentration of MEK in extract phase. So if you look at here, mole concentration you cannot find. But the mole concentration we just specified on the property set. So you go stream property, stream dash property. So this one, just take note. And stream is, we are looking at mole concentration of MEK in extract phase. Somebody take a photo, very smart. I don't know whether it's a smart or not. You take photo, that's the answer. As I said, you rely on answer, it doesn't help you much. We need to define another variable to find out partition coefficient. JC, what?
Solubility of MEK in the raffinate stream.
Wonderful. Well, in other words, mole concentration of MEK in raffinate phase. So we need to define two variables here. Okay, so we are looking at stream property. In this case, raffinate phase. We are looking at mole concentration of MEK. Okay? Make sense? Now we can calculate. What is our partition coefficient? Simply this one divided by this one is partition coefficient. You can do in the outside mass pen or I don't like it. We can do simple math in Fortran. So if you look at here, there is called Fortran tab. Have you seen this tab? No? Let's go Fortran tab. This is called Fortran. Fortran available in mass pen. And the basic statement says executable line start from column 7. So if you look at here, it's column 1, 2. You get here column number 3, 4, 5, 6, 7. You can start from column 7. Executable statement begins problem 7. Okay? As I said, we use Fortran for simple math. What we are looking for, we are looking for partition coefficient. Then we are looking for log of partition coefficient. So KOW, that's the partition coefficient. But when you name variable, this is double variable. You have to put some character, A through I, O through D, for double variable. I use D for double variable. Okay? DKOW or partition coefficient, we just defined the variable mole concentration of MEK in extract phase divided by mole concentration of MEK in latent phase. That's the partition coefficient. Experimental result is log of this, so D log KOW should be equal to log 10, because in Fortran, base log is log 10, natural log is just log. Okay? We use base log, okay? So log 10 DKW. That's good.
You said double variable, is that because it's dependent on the two variables that we define?
So double variables, real variables, which is fraction, decimal point.
Wait, can you say that again?
Decimal point.
Oh,
Integer, whole number, no decimal. Double or real variable with decimal point. You didn't know MATLAB? Real variable, double variable. No, that's not good. You know integer variable. Integer, whole number, no decimal point. Real variable or double variable with decimal point. That's simple. But page, don't be cheap. If you don't ask, even though you don't know, that's simple. Page, make sure. If you don't know, just make sure. Because I assume you know it. Why? Designer when I was senior, you all took all classes, man. That's why, I assume, my assumption based on. So I assume you know those things, so I go fast. But if you don't know, just don't worry. Stop me anytime and make sure.
This is not tabulate tabs missing.
Okay, so let's go tabulate. Now, we define the new variables, eh? So you have to type it. Job, you have to type it what you define. DKOW. So I defined the DKOW. Okay? And I also define the log KOW. It doesn't show up automatically. You define those variables on the Fortran, you have to fill up that variables. So template. Okay, let's reset. Hopefully we don't have any warning or error. Hopefully. Oh my goodness, I'm lucky or skillful. Make sure your typo is very important. Whenever you use software, you know MATLAB, typo, very important. Make sure. Whew. What do we got? We got DKOW and D log KOW. Simply partition coefficient and log partition coefficient. We are comparing these values, okay, to experimental value. What was the experimental value, Lillian?
What, I'm sorry? The experimental.
Log KOW of experimental value. Or experimental value of log KOW. Log partition coefficient.
The numerator of the partition coefficient, is that what you're asking for?
I am asking, so we have some information from literature review.
Was it the flow rate of the MEK?
No, I am asking what was the value of log Cartesian coefficient?
Was it 0.49?
0.49. Okay. Don't worry. Let me show you. So if you look at here, the experimental data, not really, the experimental data of log KOW is 0.49. That value is from literature review, simply. Literature review means some engineers, they did the experimental work to find out that log KOW. We are using Aspen to simulate same thing. That's what we found out here. So these values should be close to 0.49. What property method did you use that, Lilia, for this simulation?
RTL.
We used the NRTL. So we used the NRTL. Our first objective is carry out this sensitivity analysis to find out the best property method. We used the NRTL, produced this log KOW approximately 0.77, 0.78. We are looking for should be 0.49. We are close to 0.49. Okay, let's look at different properties. So I got different property method, go to properties window. Okay, the default is NRTL. Now we can choose maybe Unipack. Let's choose Unipack. Okay, I choose different property method. I reset. So now I chose Unipack property method. Yes? Yes? Okay. Now we can look at it. What is that the log KOW value is? Make sure. So I can look at it our sensitivity analysis. What value you observe?
Like 0.6.
0.56, something like that. So Unipack property method produce better than NRTL property method. So far, you can see this about 0.6, 0.63. Can we try other property method? Okay. Now I go back property window, and then I can choose different property method. Maybe we can look at it Unipack. Yes? Okay? I come back simulation window. Then I can look at our result, sensitivity result. What value do you observe? Close to 0.49. So among these three property methods, we found out where Unipack produce the closest value to experimental result. Right? Is it clear? Yes? You need to submit this screenshot for your home submission. 3 different screenshots. 3 different property methods. 3 different screenshots. So we found out where Unipack is the best property method. So we can use that Unipack property method. So our target is to set up extract. So let's try to use extract. Where is extract? If you go column, there's good extract in. That's what we are using in today. So simply I put extract. I'll name it extract, and I can connect. And in this simulation, our target is to get pure water from this laminate phase. That's our target. If you come here, so far so good. I can go next. Okay, this is the input specification for the extract block, a new block. But The requirement is very simple. Number of stages. That's the only requirement. But we don't know what and where. Maybe you can assume guess any number. 4 or 5. Let's look at it. 4 number of stages. Key components. First liquid phase is water. Second liquid phase is octanol. And pressure, we have 4 stages, but we can define only stage number 1, 180 atm temperature, also 25 degrees Celsius. I just specify stage number 1. And do not be afraid of. Now information is given, you start from guessing. Just guess any number. What we are looking at, lactinate phase, and we are looking at water mass fraction. This one should be 0.998. So I selected the number of stage 4, but 0.9979. I think it's close enough. Oh, you don't like it, then just come back here. Oh, let's choose 5. See what happens. This only takes 10 seconds. Don't be afraid of changing anything. Lactinate phase, I am looking at water mass fraction, greater than 0.998. Our next step is to separate. This extract phase has octanol and MEK, so we want to separate. But not much information is given. In that case, how you do it, the simplest way, if you go to the manipulator, there is one duplicate. I install one duplicate, and we don't have much information for distillation column. In that case, you always start from shortcut distillation column is called dis2u. So I want to look at it, dis2u column first to find out some variables. So what this duplicate does, just duplicate this string. That's what the duplicate does. So I don't need to create this input stream again and again. Just duplicate. I can connect our input stream. There's 2 output stream. I will name it this one P1. This is called dis2u column. Shortcut. Simple distillation column. dis2u upstream. dis2u bottom. Simple go next. Okay, guidance for distillation. dis2u column specification. Number of stages or reflux ratio, either one, you can specify any number first. And component light key, we will get light is MEK, recovery maybe 0.995, heavy is octanol, maybe 0.005. You just play around it. Condenser 1, deboiler 1 or 1.1, doesn't matter. Start any number. Do not be afraid of it. What we are looking for, in this case, bottom stream, which is octanol stream, and we are looking for octanol mass fraction should be greater than 99.9%. Okay, but we get very close. We used these two for what purpose? So if you go these two block, you can click result. You use this shortcut, this 2 column, get some idea about this minimum reflux ratio, actual reflux ratio, minimum number of stages, actual number of stages. You get some of those basic ideas. Yes? We can use that range, reflux ratio range, number of stages range to do our red column design. That's the beauty of using that the 2 shortcut distillation column is. Okay? We are working on rigorous distillation column design. From these two columns, what information we got? Maybe number of stages, 4 condensers, total condenser. Not much information is given. Initially, we used the reflux ratio 2, and then we are looking for bottom product. So maybe I can choose bottom rate or bottoms to feed ratio. We don't know. Just start from any number. We can do design spec. Bottoms, right? So bottom is okay. We can do design spec later to find out what is the optimal condition. Let's look at it. Okay, we are looking at lead drop bottom stream. We are looking at octanol mass fraction. So octanol mass fraction, we got 0.999884. But if you do design spec, you can set octanol purity 0.999, and then you can find out bottom to feed ratio. What is exactly required? Any questions? We can continue next Wednesday.